Showed up for me.
Yeah,
Okay.
I see it. I see it now.
Oh, good.
Flathead
Okay.
Lake zooming in.
All right, so here's what I was talking about. Lake Pend Oreille marks the position of the presumed ice dam. You can see the faint lines here, which is the northern panhandle of Idaho. And there was a lobe of ice that came down this trench right here called the Purcell Trench, and it blocked off the flow, the northwest flow of the Clark Fork River that came out here and then drained south out over the Spokane Valley. And then, so ice dam over here in the western Montana is the lake basins. And those basins would have included the Mission Basin here. That was the biggest one that held the greatest volume of water.
You're going to have to slow down. It's not keeping up from what I'm seeing.
Okay. How about now?
Randall, you have
Yes.
that on your 4K monitor? It's going to be real slow for us.
My 4K monitor. Oh, I see.
Yeah.
Okay, so I won't move around, but if the map stays still, you can.
Yes.
It works, right?
Yes.
Okay. So I'm going to go real slow here. Are we keeping up now?
I think so.
I haven't really moved, but a little bit south to get in the
the Bitterroot Valley.
Bitterroot, exactly. Yep.
Okay, so this is the Bitterroot, which was the second largest of the basins. And then there was lots of valleys, tributaries here that the water backflooded into. But we were talking about the Bison Range. I will move it very slow. I will zoom in. And this right here is the Bison Range. And let's see. Oh, there we go. So you can see there's a windy road. Let's see where you come in. There's a windy road that goes up to the top of this thing. And there's an overlook up here that you've got this grand vista looking to the north up across the Mission Valley. And that was the biggest of the lake basins. And the floor of the Mission Valley is just thickly laden with sediment that was laid down on the bottom. But then if you go up here to the north, we get to Flathead Lake. And I'm going to zoom in. Hopefully you guys are keeping up with this. I'm trying to go slow.
Yeah, it's doing good now. Looking good.
It looks like they got some of the LiDAR in there. Even that's pretty detailed looking maps there.
Yeah.
On the Mission Mountains there to the right of Flathead Lake.
Yeah. Look at this.
Yeah.
So right here you see this wrinkly. This is glacial mooring. This is terminal mooring right here. So that terminal mooring tells us that there was a glacier lobe that came down here and it stopped right here. And it was coming from the north. The Flathead Lake, the basin of Flathead Lake, was, to my mind, undoubtedly eroded by highly pressurized subglacial floods coming from the north. All this thick sediment, the modern Flathead River, has cut its way down into these massive, thick layers of sediment that was deposited on the bottom of this basin of Lake Missoula. And it's quite, we've done some overflights over this valley, and it's quite impressive.
Well, you're zooming out. If you want to zoom in, you see it says Kerr there. That's right where the dam is, which is what's behind me.
Okay, let's.
It's a little tool down the road past the airport there to get toward the dam. Quite beautiful overlook there. Yeah, and it was gushing when we were there because there were several days of rain.
There we go.
Coming across Spokane and Idaho and western Montana. So yeah, we had some really spectacular output volume going through those dams.
This is a spectacular vantage point from which to see the Flathead River and how it's incised its way down into these massive, thick layers of sediment that cover the whole Mission Valley floor, which is totally a relic of the huge amount of water gushing in and filling this basin. But this water is saturated with sediment that it's picked up in its route at the bottom of the glacier, the bottom of the Flathead lobe. So
And
yeah,
you're-
that's the
and
Flathead
you're
River.
more or less back out a little bit there, Randall. You're more or
Yep.
less also at the edge of the moraine, right? So I would think that's very possibly like a subglacial outburst point, and then you go
Yes.
right into that Buffalo Basin there,
Yep.
where all those boulders are. Yeah, I think it's very similar in that way to Cabinet Gorge that we looked at in one of the recent podcasts. Also, it could have been a glacial outburst,
Yeah,
subglacial outburst point right near where those dams are.
and Cabinet Gorge is on the itinerary for this trip.
Yes, sir.
Cool. All right, look, check this out. Here you can see the very distinct transition between the moraine and just beyond the moraine, where it's still possible to do agriculture. But the moraine itself is too bouldery, too hummocky, too irregular. But then north of the moraine is the town of Polson. So this moraine here is called the Polson moraine. And what Brad was pointing out is if you follow this moraine over here, you can actually see where the Flathead River breaches the moraine. Let me go back to right here. You can see that the Flathead River breaches the arc of moraine coming across. So Brad's 100% right. This is undoubtedly one of the breakout points for this water coming from the north. I'm going to zoom back out. And by the way, there is a monster that lives in the Flathead Lake. So I don't want that to deter anyone. As far as I know, it does not it does not eat humans. I mean, it has in the past, but it's been a while. I don't think it's actually consumed anyone for at least 10 or 12 years since. Okay, now look, as I'm getting north, you start seeing the first traces of a drumlinized landscape. Look at this. Are you seeing this, Russ?
Yes.
Yeah, you can see the first you see the drumlins starting to show up here. Look at this over here.
Oh, yeah.
Now, those drumlins, I'm completely convinced that John Shaw was right. The drumlins are created by water flowing under the glaciers, under pressure, and not directly by the glacier itself. I do think that there's a two-part process to the creation of the drumlins. First part is the glaciers, because the glaciers come through and they pulverize the ground, the land beneath the glacier. They pulverize it and smash it up, break it up, get it all, everything from sand to gravel to cobbles to boulders. Everything is mixed indiscriminately with no kind of structure to it. That's step one. Glaciers come in, they pulverize, they grind up the landscape beneath the glaciers. But how you get from that to forming these elegant boat hull shaped aerodynamic forms has been the point of contention for 150 years at least, with dozens and dozens of theories about how the glaciers could actually do this. Then John Shaw comes along and says, well, it wasn't just the glaciers, it was the water flowing under the glaciers, flowing under pressure, that then was able to hydrodynamically reshape that ground mass that was prepared for it by the glaciers moving over the land. So look, as we continue north, you'll see drumlins. See, look at this.
And you do have both in that trench. That just amazingly huge Rocky Mountain trench that goes over 1,000 miles up into British Columbia. There are bedrock drumlins and there are sedimentary drumlins. There's both.
Good point. Yes, there's both. And we've seen many examples of both.
Yep.
Because the flowing water, obviously, whatever the material is, the density, compactness, cohesiveness of the material is going to affect how it ends up taking on this hydrodynamic geometry. But yes, it will eventually it'll create the same thing. It'll be blunt on the upstream edge, generally tapered on the downstream. So look as we're going up, look at the floor as we're going up the trench. Now what glaciers tend to grind things off. So if you've got knobs and irregularities and hummocks and all of that, generally what a glacier is going to try to do, and does, is it starts grinding down the high places, filling in the low places. We're looking at here is a topography that definitely is not created only by glaciers. Yeah, here we go. Now we're starting to get into the serious drumlins. Look at this. And you see, notice the blunt upstream end. Yeah, there's hundreds of them, probably thousands up in the trench. And we had this discussion. Bradley and I had this discussion before we ever went up here and before we'd actually seen the digital maps, and said, okay, if there was a water flow coming down the trench along the model of John Shaw, there should be drumlins. We look, and sure enough, there they are. There they are. So we can zoom out.
And this is such a gift, though, to have these maps, because you drive up that road 93 there and you can't tell what's going on. They're forested over. You can't see. Even if you got the drone flying, you don't really pick stuff out. But looking at these topo maps,
yep.
Yeah, it's so obvious there was something major happening through this valley.
And see, what I want people to realize is that this is just like one example of a landscape that has lain hidden for thousands of years that nobody has seen for exactly the reason Brad said. Although in the immediate wake, in the melting away of the glaciers, basically you're going to be looking at a barren sculpted landscape without vegetation, without the forests. But once the forests came back, sometime presumably during the climatic optimum 8 to 10,000 years ago, they've been covered in forests ever since. So this landscape formed by these huge pressurized floods has been hidden. But now it's revealing itself, and we can see it. And there it is, the mute evidence that there were these tremendous flows southwards. And that is why I maintain that what we call Lake Missoula, and this has nothing to do with the chronology of the filling and emptying of these basins and the timing, which still needs to be worked out in detail between the mode where this landscape to the north was under full glacial mode to where it is now. Because the thing you got to realize is that all of these valleys, at the time we're talking about here, these valleys, the Rocky Mountain Trench, for example, probably had between 3,000 and 4,000 feet, easily, maybe more than that, of ice, glacial ice. They were filled with glacial ice. All of these mountains were mostly covered with glaciers. And essentially all you really saw was the peaks of the highest mountains during the peak of the Cordilleran ice sheet, which is what covered this landscape here. So all of that ice that was there, and we're talking about hundreds of thousands of cubic miles of ice. It's estimated that the entire Cordilleran ice sheet was more than 1 million cubic miles. Bigger, probably, than the ice sheet that now covers Greenland, okay? Which is a useful analogy here, because North America had two ice sheets. The Laurentide, which was the bigger of the two, centered roughly over Hudson Bay, that might have been up to 1.5 miles thick, maybe thicker. And then we had the Cordilleran. The Laurentide, its modern analog, is Antarctica, the South Polar ice cap. The Laurentide probably had more ice than Antarctica does now. Of course, back during the late glacial maximum, it's likely that Antarctica also had more glacial ice than it does now. Then, by contrast, the Cordilleran ice sheet is very similar in its size and scale as the Greenland ice sheet. So now think of this. If we go back, and we're not even talking about the Fennoscandian ice sheet, which is over northwestern Europe. That's not even part of the discussion. When you add that in, easily during the late glacial maximum, 15 to 20 to 22,000 years ago, somewhere within that range, there was more than double the amount of ice in this world, on this planet, than there is now. Okay, all of that I said to disappear. This entire screen that you're seeing here was buried under glacial ice, right? It all had to go away. It's gone. We don't see it there now. So it had to have melted, and when it melted, where did it go? Well, there's only ultimately for all of this water that heads up here, like Rocky Mountain Trench. You'll see the Rocky Mountain Trench. Over here, you see the Purcell Trench. We come here further to the east, and we've got the Okanagan.
You're going west.
I missed one. I missed one. The Columbia. Did we catch up yet?
Yeah, it's poking along on my end, but yeah, you're going west there. But yeah, don't stray from Eureka. We still want to show that field to drumlins because yeah, we might be literally reworking the itinerary as we look at this, because if you notice that route 2 to 37 there goes straight up into Eureka, so we may take off and detour from Kootenai Falls and go straight up into the drumlin fields and then down the Rocky Mountain Trench back into Flathead Lake. That would be pretty spectacular.
Yes, it would. And there are drumlins.
We got space for about 30 people, probably less than that at this point. So we'd love to have people out there. It's always a great time. We're looking at 6 days, September 18th to 23rd. Start making your plans now.
So you're talking about taking this route 2?
Correct.
Up along the
right between Troy and Libby is the Kootenai Falls there, and then we jump off at Libby and go 37 and go along that lake. That's beautiful. I've been part that way, right up into Eureka, and then come down the Rocky Mountain Trench. So yeah, we're not backtracking that way.
Oh wow, yes.
Oh man, that'd be a hell of a day.
Oh, wouldn't it though? Wouldn't it? All right, so Matt, you feel like you know a little bit more about drumlins now than you did before?
I do, and you have convinced me to join this trip, and I want every one of you watching now to buy your tickets.